Good morning, everybody. Thanks all for joining, even live, but also remotely, if there are any people, hopefully. I'm looking forward to this, to have some fun with coroutines. My name is Riccardo Lippolis. I'm from the Netherlands, Rotterdam, to be exact. I work for the Port of Rotterdam currently, where I do awesome stuff with Kotlin and coroutines, building a routing engine for containers, not the Docker variant, but the actual containers. So you can imagine that performance might be a thing there. I've been doing Java for more than 10 years now, and the last 3 years approximately switched to Kotlin, where I've also basically taught myself how to work with coroutines. Furthermore, I've been doing talks about reactive programming and Kotlin already, so switching to coroutines was kind of a natural thing for me, and maybe later on you'll see why that is. Colleagues are calling me the Kotlin hipster. That's why I was wearing the checkered shirt at the previous talks. But yeah, I feel like hipster has lost a bit of its hip vibe lately, so stopped wearing the shirt. So yeah, what's a coroutine? Basically, it's about a number of things. I've looked up the definition. So the first thing you see is non-preemptive multitasking. So when I see that, it's like, okay, why would I want that? Like, what's that? What's different about it than the regular multitasking? And the second thing is that you see is that functions can be suspended and resumed. And coming from the Java world, I'm like, yeah, how do we do that? I mean, we used to have a thread.stop method that was taken away from the API, and for good reasons, of course. But so how do you do that? Like, I mean, if you call a function, then you can only wait until you get the result, right? So what's going on there? So let's start with non-preemptive multitasking. Of course, again, a long definition, but I mean, it's just about the keywords here. It's about multitasking without with as little context switching as possible, and context switching in the sense of a thread context in the case of coroutines. So basically, it's about doing multiple things in the same thread context, and that only works when all the different tasks within that context have manners, you say. So I put the picture here of a single-track road where only one car can pass at a time, but there are these passing lanes. And these kinds of roads work when occasionally someone actually puts his car to the side and lets the other one pass. If you don't do that, then of course there's a collision or a deadlock, you might say. Then it won't work. So it's the idea is that threads give each other, not threads, but tasks give each other space to execute on the same thread. So, being half Italian, I thought, okay, how can I explain this concept? How can I learn about this concept? And I thought, well, cooking pasta might be a good idea. So I've come up with a very basic pasta dish. If you know Italians, you know that they can be pretty religious about their pasta. Even different regions within Italy, they have like these rules about what you can put in your pasta and what you cannot put in pasta. So I hope I'm not offending some other region in Italy now. But I think all of the Italians can agree that we're not putting ketchup in the pasta. Not even Kotlin ketchup, which is apparently a real brand in Poland. So yeah, no ketchup. The idea here is let's cook pasta in a traditional single-threaded, normal Kotlin way without using coroutines, where I've basically color-coded each of the steps. You'll see later why I did that. But it's a simple dish, you know, like boil some water, cut some vegetables, prepare the sauce, add the salt to the water, boil the pasta, and at the end, you put everything together and you serve the dish. how I've implemented the boil water and basically all the other steps just using thread.sleep. I mean, it's not about actually doing something, but just by showing the concept. So it's really, really basic implementation just to have some different steps that take some time. So you can already see here that some steps are belong more together than other steps. For example, these 3 steps that I've highlighted here, they're about concerning the pasta, basically. And there's a part that's basically the sauce. And then in the end, you have these 2 components, and you put them together. So you already see there are some dependencies, basically. But because, of course, we're just running it all on a single thread, it's all done sequentially. And you'll see that when we've executed here, you see the colors here that relate to the different steps that we were executing. It's all executed on the main thread because, well, we did nothing wrong, nothing weird with threading. And you see the different steps, each executed sequentially, exactly how you would expect it to have behaved. And it runs in about, well, in this case, 35 seconds. I mean, I'm not a fast cooker. The 35 seconds is just some random number, but basically it's the sum of all the thread.sleep steps in the previous piece of code that I showed. So how will we do that with coroutines? Basically, it's still sort of like an imperative flow, but you can see here that we've grouped some tasks together. And I'll explain what everything means, because you see some new things here, like a suspend keyword and something with coroutine scope, and I'll explain all that later on. And it's, in the implementation of the different steps, they're also suspending, and you'll know why later. You see that instead of a thread.sleep, I use a delay, which is a helper method from the Kotlin Coroutines library, which is basically the same as thread.sleep with one major difference, that it's not blocking. And why that works, we'll learn later. So, like I said, the steps necessary to create a pasta, we can group that together. And we use the async keyword here, which is also an extension function, a function from the Kotlin Coroutines library, which basically says, I want to execute this piece of code asynchronously, and I get basically a sort of like a future or promise, which is called a deferred back, and that's the pasta. So it's not directly fully executed, but you get an async reference to that piece of code. The same for the sauce, you know, cutting the vegetables and preparing the sauce. When both of these steps are done, then we have our sauce. When we have multiple async pieces of code and we want to wait until all of them are ready, we can say, OK, await all. That's also a helper function in the library. This will basically block, not really block, but suspend until all of the results from the different pieces of async code are ready. And we end with serving the dish. So let's execute this. And what we see here is, well, I mean, when I first, well, not running this particular piece of code, but when I was first working with coroutines, my mind was blown. Like, how is it possible that these steps now somehow intertwine? You know, like you have the boiling water and the cooking the pasta that was basically intertwined with the cutting of the vegetables and all the other steps necessary to make the sauce. And it executed in a lot less time. I mean, it's now 20 seconds instead of 35. I mean, 35 was already pretty fast for a pasta dish, but 20 seconds is amazing. And what's also weird is that this was all executing on the same thread. Like, how is this possible? I mean, we just write an imperative block of code, and all of a sudden it's not executed sequentially anymore, you know, like you're used to. So for me, it was magic. I mean, my mind was blown. Well, this is where the concept of suspending functions comes to mind. So, like I said before, a suspending function that can be paused and resumed, and they can also wait at certain points without blocking. So how does that work? Basically, when you want to create a suspending function, you use a suspend keyword in Kotlin, and suspend is the only language feature in the Kotlin language that's added to be able to use coroutines. All the other stuff for coroutines is all in the Kotlin Coroutines library, but the suspend keyword is the only language feature. And other than that, it's all in the library. So when do you suspend? Well, when you call a delay method, and like I said, delay was like thread.sleep, where it's delays for at minimum the given time in milliseconds, and like threads, it's also minimum, but usually it's pretty much the exact time. But of course, when there are no resources to fire up again after the delay, then it won't. But in practice, normally it's that given time. You have the yield method, which basically says, okay, at this point in my code, I'm prepared to give control to another coroutine if there is one with a priority that needs to do something. You might use that, for example, if you have a coroutine where you do a big calculation and then at certain steps within the calculation you say, oh, I can yield for a moment to not use too much of the time on a specific thread. And when you call another suspending function, that's also a point where your function may suspend. So you might think like, okay, but how does it work under the hood in the engine? Like, how can my function stop here? Well, that's actually the reason why the suspend keyword was added to the language. Basically, when you write a suspending function, under the hood, the JVM bytecode looks totally different than your function. If we have some time at the end, I can show it, or if you're interested, you can come to me and I'll show it. It's pretty mess because, of course, it's bytecode translated back to Java code, so it's ugly. But yeah, basically your function doesn't look the same under the hood, but that makes it possible for your function to basically be executed in separate pieces up until every suspension point. So looking at the cooking pasta again, because we call delay here in the boil water function, that's the point where our boil water function can suspend. So at this point, the main thread was executing the boil water function, and it comes at the suspend point, and it knows, okay, now I can stop executing this function for at least 5 seconds. And that gives way to the getVegetables method to execute. So basically, that's how on one thread you can do multiple things. So I've talked about the suspend keyword. But you also see the term coroutine scope. So what's a coroutine scope? I mean, that's also might be a weird thing if you haven't worked with coroutines before. But basically, the concept of coroutine scope is best explained by explaining the term structured concurrency. So structured concurrency, it has a big definition. I won't let you read it. It's like, I'll give you the basic version. Like it says, structured concurrency, you can structure your concurrency by using imperative program flow. So like we've seen, with imperative program flow, I mean you can just call methods, they have return values, and you can call other methods that call other methods again, and you can use for loops, etc. Like all these basic program flow operators you're already used to when you're programming normal single-threaded code. And like in normal programming, when a parent function calls a child function, so when you are calling a function, your function will not finish before that other function is finished. Because if you're in class A and the function X and you call function Y, then you wait until the return value of Y comes back until X can finish. That's like pretty basic knowledge when you're using imperative flow. And the same thing applies in coroutines with structured concurrency. So when you have, for example, like before in the pasta dish, when a function calls an async function on another, asynchronously calls another function, that whole function block will not finish before that asynchronous task is actually completed. And that helps to structure your whole application in a way that it's still readable, but can also be executed asynchronously. Errors in child jobs, they propagate to parent jobs. And when you have multiple child jobs and one of them fails, then the other child jobs will get canceled. So you won't do anything like any calculations or calls that are no longer needed because the parent job has already failed due to failure of one of the other childs. So when you do multi-threaded work with, for example, some thread pool where you manage the threads yourself or the tasks you execute on the thread pool, and one of the tasks fails, you're responsible yourself to clean up all the other tasks. So basically, technically, you can do the same thing with threads and thread pools as you can do with coroutines and, basically with structured concurrency, but there's a lot of boilerplate code needed to achieve the same level. And with structured concurrency, that's all a given from the library itself. So that makes it more convenient. So what does that mean for our pasta? So I've structured the application a bit differently now, the recipe. I have the prepare pasta and the make sauce functions. They basically have the different components of the pasta dish that we are making. And I have one function that says, OK, prepare the dish, which is using the coroutine scope keyword to define a block where I can launch a synchronous task. So coroutine scope basically gives you a context in which you can call launch and async, the functions we saw earlier, where the difference between launch and async is that launch doesn't have a return value and async does. So earlier on, I was cheating a bit with the async because it was basically returning a unit, which is basically the Kotlin equivalent of void. So I could have used launch as well, but for the readability, I used async there. But in this case, we just say, OK, we launch the preparing of the pasta, and we launch the making of the sauce. And because we're using structured concurrency, what happens here is that the whole prepare dish block function will only finish when both of the async tasks that it's called are actually finished. So the whole prepare dish function is not finished until both the prepare pasta and the make sauce functions are actually finished. So that means that the serve dish method or function you see here, because it's after the prepare dish function, will only be called when both the pasta and the sauce are ready. And that's basically how you expect it to execute if you read it, right? But still, you have asynchronicity, but it's still readable. So how does it work with error propagation? Like I said, when there's a function somewhere in the child of a coroutine scope that fails, then it propagates up to the parent, and the other jobs are cancelled. So if we have the boil pasta dish and we function and we throw a normal exception there, which of course should never happen, but hey, we all know those kinds of exceptions always happen when you state that they shouldn't. So yeah, well, what happens is exactly what you expect. You see the exception in the stack trace in your logging, and the cutting of the vegetables, which was started on the second line, doesn't get finished because I mean there's fire. Stop cutting vegetables, and go put it out, right? And that's yeah, also very nice, so that you, as a programmer, you don't have the responsibility to clean up all those tasks that you spawn, but basically it's all done for you. And of course, there are also ways of, for example, doing resource cleanup, closing resources, etc. But also, if you have more like a parent job that it should always run and it spawns multiple threads, and you don't want one of the spawns multiple coroutines, and when one of them fails, you don't want the others to fail. There are also mechanisms to define a sort of like it's called a supervisor scope, where the parent will never be killed by its child, which sounds very ominous if I say it like that, but I hope you get my point. So yeah, so far we've all done everything single-threaded, which is already amazing, right? Like doing multiple tasks on one thread simultaneously. But can we use multiple threads? Well, yeah, and with a slight note that if you're using Kotlin JS, the JavaScript variant, then no. Because, well, JavaScript that runs single-threaded, and with Kotlin native, there's also there's a default way of working where it's single-threaded, and there's also a multi-threaded way which has some pros and cons. So they're not using that by default yet. So if you're using Kotlin native, yeah, read up about it. I haven't used it. I'm mostly focused on the JVM. But in Kotlin JVM, yeah, we can do it multi-threaded. So to explain how to do that, I have to start with explaining the concept of a coroutine context. All coroutines, they are executed within a certain context, and context, of course, is a pretty vague concept. It's like everything around you. And it's, well, basically, you can compare it to thread context in Java, or like a request context in Spring. You know, that's like there are some elements in your coroutine context which you have access to, and they also determine a part of the behavior of your coroutine. So you can see that like it's like a map of key value pairs where some information about your context is stored. So one of the elements in the coroutine context is the dispatcher, and the coroutine dispatcher basically defines on which thread or threads your coroutine will run. And there are a number of different dispatchers, and you can create your own, of course. And when you call a suspending function from another suspending function, that coroutine, that's the child, basically inherits the context of the parent. So you don't have to define everything every time again, but you can write a suspending function, and then depending on from what context it was called, it can behave slightly different. But if there are some requirements for your coroutine, you can override the context of your parent when you're being called, and then you're overriding it for yourself and the child coroutines below you. But of course not for your parent. So how do we do multi-threaded pasta? You see here we're using the WithContext function, and we specify dispatchers.default, which is one of the dispatchers that's readily available from you. But you have to keep in mind that even though it's called default, it's not used by default when you're using coroutines. And basically, the default code dispatcher that you're using depends on how, basically how you start using coroutines, but we'll get to that later. But just keep in mind that even though it's called default, it's not like it's always being used. So the WithContext method or function, you can say it's pretty similar to coroutine scope. You define a block, which is your coroutine scope, but you add some additional context to your coroutine. So I was a bit confused when I first saw this method because it says WithContext, but I pass in a dispatcher. So like, is a dispatcher a context then? But No, it's basically saying that you enrich the context with a dispatcher. So when we execute this, well, we see, hey, multiple threads. Wow. You can see that the boiling of the water happens mostly on worker 2. The cutting of the vegetables, you see that it's working on another thread. And the serve dish is executed on the main thread again, because the function that was called with the coroutine context didn't include the serve dish. The serve dish was in the parent function, so the parent is still on the main thread like before. But what's a bit odd is that both the creating of the pasta and the serving of the sauce, they both run on the same thread. But hey, we specify like, hey, should execute on multiple threads, and we saw that like the worker 3 and worker 2 are used interchangeably. So why is all of a sudden both the pasta and the sauce on worker 2? Well, even though it starts out on a certain thread, that doesn't mean that the coroutine is confined to that thread. Basically, after every suspend point in your function, when it resumes, it may resume on another thread, basically on whatever thread is available. And because, well, after the pasta was ready, the worker 2 thread was still available for work, the Coroutines library decided to finish up on the same thread with the sauce. That helps in not continuously switching threads while performing work. Basically, when a certain coroutine is suspended, then immediately the thread will seek out new work, and that makes it efficient. Sorry. So, what dispatcher types do we have? Well, I started out with the dispatchers.default. It's basically a shared thread pool that's confined by the number of CPU cores you have multiplied by a given number. And you can compare it to the fork join pool that's in Java. It's basically the same concept. It's a standard pool for executing your coroutines, which is given to you by default, hence the name. There's an I/O dispatcher, which is convenient for offloading I/O tasks that might be blocking, or, well, basically they don't do a lot of work, but are mostly just waiting for a response. And I say blocking, but of course you can prefer to use non-blocking I/O, and you can, of course, use the I/O dispatcher for non-blocking I/O as well. But it's basically an offloading of threads, or like, a task to a dispatcher, which basically just says, okay, it can grow beyond the default dispatcher, because, I mean, if you have a lot of sleeping coroutines, you can just place them on the same dispatcher, because they're not doing anything anyway, just waiting for response. So it's not like with the threads that it takes a lot of memory. There's a dispatcher.main, which is only when you're using UI development on Kotlin, then it might be convenient, for example, with Android or Swing or JavaFX. Well, if you're doing UI development, you know that updating the UI must happen on a certain UI thread. And when you're doing something blocking, like network traffic or disk loading, you definitely do not want to do that on the main on the main UI thread. And, well, the Coroutines library by default gives you support for that. So if you're using Android, JavaFX, or Swing, you can use the dispatchers.main to basically run your coroutines which update the UI on that main dispatcher. But when you're doing I/O, you can offload it to the I/O dispatcher. But what's convenient is when the UI has to wait for a certain data to be loaded from disk or from some network resource, the coroutine running on the UI thread can basically suspend. And that means it won't block because, well, it's suspending, so it's not actually blocking the thread. And that's, convenient, because you can just await some coroutine which is executing an I/O thread, and while that is happening, the UI thread can just continue with doing other work instead of blocking the UI. You can also just create a typical Java executor and convert it to a coroutine dispatcher. There's an extension function for that. So you can just create, for example, a fixed thread pool and make a coroutine dispatcher out of that if you want to limit the amount of concurrent tasks happening, for example. So yeah, we talked about how suspending functions can be called from other suspending functions, and coroutines are always executed in a coroutine context. But yeah, how do we get there? How do we get from the typical blocking code we've always been writing to the new and hip world of coroutines? Well, there are a number of ways. I'll start out with one of the worst ways. There's a thing called global scope, which is part of the Coroutines library as well. It's, like the name says, it's a global application scoped coroutine scope, where you can offload your one-off asynchronous tasks to. This is the only one that does use the dispatchers.default by default. So how do we do that? Say we have a save method which saves a certain entity to a repository, and it also wants to send out an event saying, "Hey, this entity is updated." I'm forgetting the whole transactional stuff here for a moment, which, by the way, I'll come to that later as well. But if you're using transactions by default in a non-reactive way, transactions often use like thread local context stuff that doesn't match well with Kotlin. So if you're with coroutines. So if you're using that, then probably you want some reactive library, which I'll come back later. But for now, just forget all about the whole transactional stuff for a moment. So we're using here global scope.launch, which basically says, okay, launch this task asynchronously on the default dispatcher and return immediately. And your event gets published. However, when something goes wrong, when there's an exception inside that launch block, you will not see that in the context of calling the save action, because the save action just succeeded. So your exceptions might get lost somewhere in the void, or in your logs you'll see them back, but it's difficult to relate them back to where they actually came from. And there's also not really a way of recovering from that. So that's one of the downsides of using global scope.launch. You can also get a return value when you use global scope.async, which returns, like I said before, deferred, which is like a future or a promise. But the thing is, when you have that deferred, you still have to await until the deferred is actually completed. And of course, you can use it like a for loop or something, but that's a terrible choice. So you still need to call await, which is a suspending function. And yeah, when you're still not in a suspending context, in a coroutine context, you cannot call that. So instead of using global scope, it's preferable to create your own coroutine scope. There's a function called run blocking, and when I first saw it, I thought it was a bit scary because I thought I don't want to block, I just want non-blocking cool stuff. But actually, it's a valid name because when you call run blocking, which is also a function where you can supply a block of coroutine code, basically what that means is that the thread you're calling the run blocking method on will block until that function call is done. And basically, I mean, that's the same thing when you're calling a normal function, right? When you call a function, the thread you're calling that function from is blocking until that function is done. So it's not that scary. It's a pretty convenient method. So it runs single-threaded, like I said, but basically that means that it runs on the thread that you're calling it from, but you can also specify your own dispatcher, but then the thread that originally called the run blocking function will still block until the whole thing is done. So, for example, if I want to offload the saving of my entity and the sending of the updated event to the I/O dispatcher, but wait until the whole thing is done, then I can use run blocking, where I specify that I want to use the I/O dispatcher. And I have two separate launch blocks where I say, OK, launch the saving of the entity and launch the sending of the updated event. And both of them will execute on the same time, at the same time. And when they're both done, then the function will return, and it's done in its entirety. And if one of the tasks fails, then the other will be cancelled. And of course, yeah, with asynchronously, you never know which one is actually executed first. So it's not the proper cleanup, of course, but just to prove the concept. And when I want to return data, I can first call the async method where I do some call to HTTP client, which is done asynchronously. Of course, here I should have used the I/O dispatcher, but I haven't. Something to fix. And while that HTTP client is waiting for its response, I could do some other stuff, and then at the end, I call the await, which basically returns the value if it's already there, and if not, it suspends until it is. And then the whole function will be done and returning the data. Ideally, you want to be like fully non-blocking from front to back, and if you want to do that, then it's convenient to use the appropriate libraries for that. So Spring, of course, has some reactive libraries which are used to do non-blocking I/O on both the front part, like the REST interfaces, as well as on the back side with the database integration. So at the front, with the REST controllers, you have Spring Web Flux, which is the reactive variant of the Spring Web MVC, which does non-blocking I/O when handling your requests. And at the database side, instead of using JDBC, you have Spring R2DBC, which is the reactive relational database connection. And that has non-blocking I/O to the database. And the fun thing is, the nice thing is that Kotlin Coroutine support is built in for both. So instead of using I don't know if you guys are familiar with the reactive programming, but there you have a concept of a mono and a flux, which are reactive streams. And when you're using WebFlux and R2DBC, stuff like that, you have to use those concepts to connect your front end to the back end and do, and all of that is basically hidden away if you're using Kotlin Coroutines, but because instead of returning a mono, you can just write a suspending function, and the function will suspend until the mono result is available. And instead of using the flux, you have the concept of a flow, which is basically the same with some minor differences. So yeah, if you're using a REST controller annotated method which does a post or a get, then you can just make it suspending and it will work out of the box. It will just run on the same I/O threads that supplied by, for example, Netty. And when you're calling the R2DBC backend, then instead of having to do something with the mono that comes back or flow, you can just call await, and that will convert it to a suspending function as well. So yeah, basically there's interoperability with the different reactive streams library. Of course, Spring uses Project Reactor, so that's a given that if one works, the other works as well. And if you're using something else in Spring, for example, Ktor has, I'm not sure if that's the right pronunciation, but hope so. It has by default also non-blocking I/O, and it also has an excellent integration with Kotlin Coroutines. And of course, there are also other libraries. So what more fun can we do? I see that there's almost 10 minutes left. So, okay. Coroutines are very lightweight, so sorry for the layout, but it's due to some resolution issue. So say you have like 100,000 tasks you want to do at the same time. If you do that with default threads, you can imagine that it takes a lot of memory, because every thread that Java spawns has a certain amount of memory needed to be able to start it and execute it. So at the top, we see that we're launching 100,000 threads. And you see at the right side, the graph shows that, well, the memory spikes pretty high. Well, of course, relatively high. And in the end, it dies off. But at the bottom, when we're using coroutines, you see that the memory is like very low, and that's because, well, basically in this function we delay a lot, so we don't need as many threads to execute this as we do well, with normal threads. Basically, we can do a lot of different tasks on the same thread, and well, spawning coroutines themselves don't take that much memory into account, like compared to threads. So that's actually pretty nice. Well, I've mentioned it before, they're cancelable, so when an exception occurs, coroutines can be canceled, but you can also cancel them manually. And like I said before, previously we had thread.stop, which was pretty a dangerous method to stop your threads. But with coroutines, you can just call cancel. And the way it works is basically when you call cancel, then the first point in time where your coroutine is going to suspend, that's the point where the coroutine library says, okay, we'll stop executing from here. There will be a cancellation exception thrown, and it will stop. So in a clean way, you can cancel your coroutines. But of course, only if you're suspending enough in your coroutines. So I mentioned the flow before. It's basically the comparable to an observable. If you're familiar with reactive programming, then you'll know the concept. If not, observable can be seen basically as an asynchronous variant of a Java stream. So it's a stream of data where each element in the stream may occur somewhere at some point in time, instead of the default stream where all the data is instantly available. So you can create a flow, you can emit items on that flow, and then another coroutine can just do filter, map, collect, like the typical operations you expect from like when you're familiar with Flux. But one point which is nice is you can, this one. When you're creating, for example, a hot observable, which just, in this case, just produces numbers, starting with 1 in the increment, you can just use a while loop and just while true, and you just send them. And because the send method is also a suspending function, it's not like it won't start producing numbers like crazy immediately. It's just, well, it depends on if there's someone actually subscribing to that channel and receiving those numbers. So, like I said before, you can use imperative programming flow, but it's not like directly the same as actually performing a while loop. And you can have multiple consumers reading from the same producer. So it's pretty nice stuff. So in the abstract, I promised that I would show a reactive Spring coroutine combination. I think it's better if we take some time for questions as well. So I'm just showing the link here. If you guys have any questions about the library, about the application after looking at it, just come to me. Basically, what I did was create a very stupid application which has a service that calculates numbers, very convenient, and it also stores the history of calculations in a database reactively, and also it calls an external web service to determine if the result from that calculation was even or odd, because you need an external web service for that. But basically it's to show the concept of reactive database connection combined with an external web service and all wrapped up into one pretty application. So let me know if you have any questions about that one. So thank you. Are there any questions from the audience, maybe to start? Yes?
Hi. Does Spring Data support coroutines? So if I make calls to Spring Data, will they automatically be suspended?
So the question is if there's Spring Data support for coroutines. Yes, but only in the reactive variant. So so R2DBC is one of that's like the reactive variant for when you're using traditional SQL database. There's, for example, for Neo4j, there's a reactive variant which also supports suspending function. I think MongoDB as well. But so basically, the reactive variants, they have support for suspending functions. Yes, you?
How do you handle cleanup of resources in coroutine that can be suspended or cancelled?
Yeah, so the question is, how do you handle cleanup? I think I have an example of that. I can yeah, so let's see if I can, oh, the other way around. Yes, so what you can see here is basically the cleanup of a coroutine where I don't do any actual cleanup, but I just delay for a moment. So basically you use a try finally, because the moment a coroutine that is suspended is being cancelled, then there is a cancellation exception being thrown. So to be able to detect that, you can use a catch or finally, like traditionally. And in the finally block, you can say WithContext non-cancelable, which is also given to you by the Coroutine library, which says, OK, I want to execute this block even though there's a cancellation going on. And there you can do your cleanup, etc. The canceling of a suspending function is handled by a cancellation exception. So basically, when coroutine is cancelled, so in this example, well, we're just repeating 1,000 times this piece of code. So when the delay method is called, delay function, normally that would suspend the function. But when a cancellation occurs, that means that basically, well, in imperative code, the delay method will throw the cancellation exception instead of just returning. No, no, no. Normal suspension, not. No. No. Yep. You?
Yeah, so in the spring example, where you had the post and the get, and you just added suspend. Like in spring, if you've got a post and you've only got 10 threads running, you can only have 10 HTTP connections. If I just put suspend, does that mean I can therefore actually, service more connections? It's still limited to spring after data.
Yeah, so the question is, when you're using the suspend function in a Spring REST controller, when you have a thread pool of 10 threads where you can execute 10 requests at the same time normally, can you now execute multiple requests on the same amount of threads? Yes, and that's basically also the concept of reactive, of non-blocking I/O, where if you're not using coroutines but using Spring Web Flux, then you have the same benefit, because Spring Web Flux uses Netty by default, which has non-blocking I/O. So also when you're using Netty, then you can handle multiple requests, like more requests than the thread pool has threads. And that's because Netty also has non-blocking I/O. So when there's an I/O call, then it also doesn't block, but suspends in a different way. And basically, when you're using Kotlin Coroutines, you have the benefit of writing less code because you can just use imperative flow, but the benefit of using non-blocking I/O is the same as with Spring Web Flux without coroutines. Let me check if there's any. How do I get to the Q&A here? Does anybody know by chance? No question? Okay. Well, thank you, everybody.